Okay, so if you're building with generative AI right now, you probably know this feeling, right? You get something working with this like perfect, super intricate prompt,
Yeah.
and then boom, you touch one thing, swap a model, add a tiny constraint, and the whole setup just breaks.
Yeah.
It's so manual, so brittle. Honestly, sometimes it feels less like engineering and more like, I don't know, guesswork.
It really does. It's the big challenge, isn't it, in building AI apps today. We need them to be reliable, scalable,
Right.
but the core interaction often boils down to getting these like natural language strings just right, and they're fragile.
Exactly.
And that specific pain point. That's why we're doing this deep dive today into DSPy.
DSPy, Declarative Self-Improving Python.
Yep, from Stanford NLP. And the promise here is pretty fundamental, changing how we actually talk to these large language models.
Okay, let's get into it then. Our mission today is really to understand this core idea DSPy has, moving from, manual prompting to actual programming.
Exactly. Programming, not prompting.
And specifically, how does it automate that, frankly, super tedious job of optimizing LLM interactions? Right. We're looking for that systematic shortcut, right, to build better AI apps faster.
Yeah, and what's really interesting is how DSPy reframes the whole thing. It stops treating prompt engineering like some kind of creative writing contest.
Yeah.
And instead treats it like a compilation problem, like compiling code.
Okay, compilation.
And that gives you this crucial separation, this decoupling. It splits the high-level logic of your AI system from all the messy, low-level details like which exact LLM you're using today or the precise words in the prompt that happen to work right now.
That decoupling sounds like a game changer.
Yeah.
So if prompting becomes compilation, what does that actually mean for me, the developer, day to day?
It means you get to work with structured code again, loops, modules, familiar programming ideas.
Oh, okay.
And you trust an optimizer, the DSPy compiler, basically, to handle the really fiddly low-level stuff, generating the best prompt. Think of it maybe like the jump developers made years ago from writing everything in assembly.
Right, very low level.
Yeah, to using something like C. Or maybe an even better analogy is moving from manually managing memory pointers to using SQL.
Oh, I like that. With SQL, you declare what data you want.
Exactly. You say what, like, the table structure and the database engine figures out the most efficient how the query plan.
Okay.
DSPy aims to do the same for prompts, which should make AI software, way more reliable, easier to maintain, and portable across different foundation models.
That SQL analogy really clicks. We're moving the hard part, the prompt tuning, from the human over to an automated compiler. So if we're programming now, not prompting, what are the building blocks? What are the technical pieces that make this optimization happen?
Okay, so DSPy pulls this off using a pipeline with three main parts. You've got signatures, modules, and optimizers.
Optimizers. I think it's something called teleprompter somewhere too.
Yeah, you might see that term, teleprompters. Functionally, they're the optimizers, the compilers. So we'll probably stick with optimizers today, just for clarity.
Makes sense. Let's start with the foundation then. Signatures. Sounds like they define the contract, the task.
Precisely. A signature is just a declarative way to specify what a piece of your DSPy program should do, inputs and outputs.
Okay.
Crucially, it tells the language model what the job is, but it absolutely does not specify how to phrase the prompt or what kind of style to use. That's the compiler's job.
So instead of me writing a giant paragraph explaining, please find the main idea of this article and summarize it concisely, I just define a signature.
You got it. It could be as simple as a string, like document bank summary.
I know, okay.
Or for more complex things, you can define fields with specific names and types, like context.list_try_r, question.stry_answer.stry_r.
Context, question, answer. And those names actually mean something to DSPy.
Yes, exactly. The field names, context, question, answer, they carry semantic weight. DSPy uses those hints to figure out the best way to phrase the request to the actual LLM later on.
And I can just write these in line or use a proper Python class if things get complicated. Like using DSPy output field to maybe force a classification output to be one of several specific options.
Yep, that class-based approach is there for when you need more detail, maybe longer instructions or hard constraints on the output. But the key thing for you, the developer, is this. When you define that signature, you focus on clarity and structure. What goes in, what comes out.
Right.
You're not sweating the exact keywords or phrasing. You let the DSPy compiler optimize that stuff because, frankly, it's designed to do it better than we can by just tinkering manually.
Okay, that flows nicely into the second piece. Modules. If signatures define the what do modules do?
Modules are the functional units, the building blocks, And they're actually inspired by PyTorch's NN module layers, if you're familiar with that.
Okay, like neural network layers.
Kind of. Each DSPy module encapsulates a specific prompting strategy or a way of executing the task. Think chain of thought or React. And here's the crucial bit. Modules have learnable parameters.
Learnable parameters. Usually that means like millions of weights in a neural net. What's learnable about a prompt?
That's a really good question, and it's core to DSPy. When we say learnable parameters here, we're mostly talking about the specific natural language bits that make a prompt work well.
Okay, like what?
Things like the perfect few-shot examples to include in the context, or the precise internal instructions for, say, a chain of thought reasoning step, or even the best way to phrase the overall system message. These are the pieces the optimizers learn and refine.
Ah, okay.
Right.
So when I choose a module, I'm picking a high-level strategy for solving the task in the signature.
Yep.
And that strategy comes with these tunable text components.
You've nailed it. The most
Yeah.
basic module is just DSPy.predict. Simple input-output.
Yeah.
But maybe your task needs step-by-step reasoning. So you could swap in DSPy.chain of thought. That module automatically teaches the LLM, hey, write down your thinking steps before giving the final answer.
And those instructions for the thinking steps. Those are the learnable parameters, the optimizer tunes.
Exactly. The optimizer might figure out that phrasing the instructions slightly differently or adding a specific example of good reasoning dramatically improves performance for your task.
And it's not just simple prediction or chain of thought, right?
Right.
I saw things like DSPy.react for agents using tools.
Yeah. DSPy React is for building agents that need to interact with external tools like a search engine or a calculator to fulfill the signature's request.
And program of thought.
Oh, program of thought is super interesting, especially for math or logical reasoning tasks. It basically teaches the LLM to output, say, Python code.
It outpicks code?
Yeah, runnable code. And then the result of executing that code becomes the final answer.
Oh.
And the beauty is how you combine these. Composing modules is just Python. You write standard Python code. You can wrap modules in your own custom classes, use loops, if-else statements, whatever.
This feels like programming.
It is programming, like building with Legos.
Hmm.
Each module is a block, and you connect them using normal Python logic. DSPy then traces all that logic when it compiles your program.
Okay, so we've got the task defined with a signature. We've chosen our strategy with modules. Now the magic part, optimization. This is where those learnable parameters actually get tuned.
This is really the heart of DSPy. The optimizers, or teleprompters, are the compilers. They take your high-level program, look at your data and your goal, and systematically tune those parameters, the few-shot examples, the instruction phrasings, to hit the best possible score on a metric you define.
Okay, so before we compile, we need a couple things in place.
Right. There's a standard workflow. First, you need a way to score the output. That's your DSPy metric. It's just a Python function that returns a score, like accuracy, or maybe something more complex.
Could the metric itself be another small DSPy program?
Absolutely. If you need to check multiple things like, is the answer correct? Is it fluent? Did it follow the format constraints? Your metric might be a little DSPy program itself.
Okay. Metric first, then data.
Then data. You need a training set. Even a small one, maybe 20 to 50 examples, is often enough to get started, especially for optimizers focusing on few-shot examples.
And I remember reading something specific, almost weird, about splitting the data for prompt optimization.
Yes. This is really important for getting stable results. For the optimizers that are refining the prompt text itself, not fine-tuning the model weights, that's different. The recommendation is kind of flipped from normal ML.
So how?
You use a small portion for training, maybe only 20%. This is where the optimizer might generate potential demonstrations or examples from. But you use a large portion, like 80%, for validation.
20 train, 80 validation.
Yeah.
Why so much validation?
Because you're not training millions of weights in a deep network. You're essentially training a prompt, often by finding the best few examples. You need a large validation set to reliably check if the examples chosen actually generalize and aren't just overfitting to the tiny training set. It prevents the optimizer from locking onto fluke examples.
Oh, okay, that makes sense. Prevent overfitting the few-shot examples. So the optimizer has the program, the metric, the data split. How does it actually tweak the prompt? Does it do the same thing every time?
No, and that's where different optimizers come in. They target different kinds of learnable parameters. Some focus on synthesizing the best few-shot examples. Others focus on refining the natural language instructions. And some can even help prepare data for actually fine-tuning the underlying LM weights, though that's a heavier process.
Let's break down the main types then. What are they optimizing? Start with the few-shot ones.
Okay, so a common one is bootstrap few-shot. This optimizer is all about finding the best data to put in your prompt.
Finding the best examples.
Exactly. It often uses your own program as a kind of teacher to generate candidate demonstrations input, reasoning steps output. Then, crucially, it checks each generated demonstration against your metric.
Uh-huh.
It only keeps the ones that score well, the really good representative examples, and those are the ones compiled into your final prompt. So optimizing the examples the LLM sees at runtime.
Got it. It's like automatically curating the perfect study guide for the LLM. What about when we need to tweak the actual text instructions, not just the examples?
Right, that's where instruction optimizers come in. Here you see more advanced algorithms like MIPROV2 or MIPROV2. It uses more systematic search techniques, often Bayesian optimization, to really explore the huge space of possible ways to phrase an instruction. It can tune both the instruction text and generate few-shot examples together, trying to find the best combination.
Okay, searching the instruction space. And the other one, GPA, reflective prompt evolution. That sounds meta.
It is. GPA is pretty cutting edge. It actually uses the LLM itself to improve the prompt.
The LLM critiques its own prompt.
Sort of, yeah. The process is like this. The LLM runs your DSPy program, looks at its own output, evaluates it against your metric, identifies why it might have failed or underperformed, and then it tries to propose changes to the prompt instructions to fix those specific weaknesses. It's iterative. The system reflects, proposes a change, tries again.
Wow.
And it works even better if you can give it some textual feedback alongside the score, especially domain-specific feedback. You're basically guiding the LLM to write a better set of instructions for itself.
That sounds incredibly powerful, but also potentially expensive. Is this kind of systematic optimization only for big companies with huge compute budgets?
You'd think so, but surprisingly, it's often quite manageable because you typically only need a small data set for prompt optimization.
Right, the 20/80 split.
Exactly. The cost can be pretty reasonable. The sources suggested a typical simple run, maybe using Bootstrap Few-Shot, might cost around, say, $2 USD and take maybe 20 minutes.
Only $2.
Roughly, yeah. Now, obviously, if you're using a huge model or running something complex like GPA over many iterations, the cost goes up. But it's often way cheaper than the equivalent hours of a human engineer manually banging their head against the wall trying different prompt phrasings.
That's a fair point. Okay, let's quickly touch on the plumbing underneath all this. Adapters. We've defined the task, chosen the strategy, compiled the prompt. What makes sure the LLM actually follows the rules?
Adapters. They're the bridge. They sit between your nice structured DSPy program and the raw API of the language model, which is often handled by a wrapper like LLM anyway.
And their job is translation.
Pretty much. They take your DSPy signature in the inputs, figure out how to format that into the specific API calls or chat messages the target LLM expects.
Okay.
And then, crucially, they parse the LLM's potentially messy response back into the structured output your DSPy program expects, according to the signature.
So if my signature says the output needs to be a Python dict with keys name and age, the adapter makes sure the prompt asks for JSON, maybe, and then parses that JSON back into the dict.
Precisely. The default is a general chat adapter, but let's say you're using a model that has native support for structured output, like outputting guaranteed JSON.
Yes, some models do that now.
Right. You can swap in the JSON adapter, and that can be a big win. It tells the LM, just give me the JSON data, which often means lower latency and fewer tokens used because you skip all the conversational filler around the data.
Lower cost, faster responses.
Nice.
And speaking of cost, it sounds like DSPy helps you keep track of that too, especially during those big optimization runs.
Yeah, that visibility is built in and pretty crucial. If you configure it, DSPy automatically tracks usage. Every time a module makes a call to the LLM, the resulting DSPy, prediction object logs things like prompt tokens, completion tokens, total tokens.
Oh.
So when you're running those optimizers, especially the more complex ones like GPA or MIPRO, you can actually monitor the token burn rate and make sure you're staying within budget. It's essential for managing costs effectively.
Okay, so zooming out, the big picture here really seems to be about making this whole process systematic, right?
Totally.
DSPy gives you these distinct pieces: the signature for the task, the module for the strategy, the metric for the goal, and the optimizer as the compiler. And you can iterate on each piece.
That's the idea. You iterate on your data, tweak your program structure, the modules and how they connect, refine your metric, or choose a different optimization strategy. It's incremental improvement.
You're basically compiling code that has these natural language annotations, and DSPy automatically tunes the LLM either through examples or instructions, to align with your program structure and your definition of success.
Exactly. It's about aligning the model with your specific needs automatically and repeatably.
So maybe the days of just randomly tweaking prompts until something works are numbered.
That's the hope. The critical skill might be shifting. For you, the developer, the next step might not be agonizing over how to rephrase a sentence in your prompt.
Right.
It might be choosing the right compiler, the right optimizer. Should you use Bootstrap Feeshot because you have a few good examples and want the best one selected? Or is your task complex enough that you need MIPRO2 or GPay to systematically search for better instructions? That choice, which optimization strategy to use, becomes the key decision. Your focus moves from manually writing the perfect prompt to defining the optimal strategy for automatically learning it.